Welcome everybody. This is a presentation on simulation, what it is. Particularly, we are going to discuss discrete event simulation. First, simulation is having the capacity to imitate reality. Usually we use a computer to do this, and it's very applied to many industries, and it's very popular and powerful. Here we have some examples of its applications. We have the possibility to represent manufacturing facilities, either actual processes or planned processes. We have the capacity to model processes within a bank, more managerial-oriented processes. We can simulate logistics, distribution, and similar operations, both from of people and goods. We can represent hospital facilities, including emergency rooms, operating rooms, admissions, rooms, and both from the perspective of the personnel, the facilities, or the patients. We can improve the operations of supermarkets, in which we have then the number of clients that we will have, the number of service lanes we need, the space, the location of the racks, etc. We have the possibility to use it in the optimization of theme parks, where long lines are created, and we want to maintain a high spirit of the visitors and a good service of the many different activities in a theme park, from the rides to the food stands to the little stores that sell the branded goods. All these can be modeled using simulation for a better experience. We can have the emergency response systems, from ambulances to firefighters to police, deciding which should be their optimal location at what times of the day. It could take into consideration the average traffic or congestion, and the nature of different type of needs within the city, depending on the type of events that could be happening. We can plan for computer networks and their workload, so those are designed in the most cost-efficient way. And just like this, there are many others. One of the advantages of simulation is that over experimenting with the system, when we're trying to optimize the results of the system, is that sometimes the model does not exist, or it would be disruptive to try to run experiments on certain models or in certain systems. It would be next to impossible to generate a real model or experimenting the system beforehand, when it's very expensive. And in those situations, it's better just to create a virtual environment. Nowadays, it's very common for us to think in terms of these virtual environments, because the digital gaming industry has allowed us to embed ourselves into this type of scenarios. So it is similar to that in the sense of this easiness to create an alternative reality, but there's more to it than just that. So we need to be aware that when we build simulation, we want to be able to measure, improve, design, and control. It's not just about having nice animations and graphics, but we need performance measures, and therefore it's more than just a game. The advantage of the models is that, well, they are not reality, so they are based on assumption and approximation to how the system works. Of course, nature will always be more complex than our models, but the advantage is that the model can be easier to understand and faster to implement, and definitely running experiments should be faster, cheaper, and safer. Also, having models as opposed to the system allows you to take risks with what-if scenarios that otherwise you would not want to run. There is no real damage when you run these scenarios in a virtual environment. And just building the model can be instructive in itself, because when we build the model, we need to understand the processes and the interrelations of the system in such a detailed way that there is a thought process that it's not usually be realized. Many of the information data set that we need when we create a simulation are only expressed as such when you actually build a simulation model. A lot of the information that it's currently stored by companies, it is oriented towards accounting or cost accounting or other performance measures oriented towards the financial reporting. But that information that is not always sufficient to create a proper simulation model that needs to account for the distribution in time of events, and what are the probabilities of one event or the other happening, or the interactions between these events. And when people have to think of those terms, they realize where might be some of the sources of limitations and constraints that the system may have in order to perform in a more efficient way. So building the model can be very instructive. One of the challenges of creating models is making sure that the model has validity. That is, regardless of the type of model, we want to try to represent reality in the most faithful way, and we want to represent reality at the level of detail that is needed. For instance, if you are modeling the operation of an office and how effective and efficient it is, you don't need to represent necessarily the exact dimensions of a desk, for instance, if it's not relevant. The benefit is that with some expertise, you realize that only it's needed to be modeled to the granularity that is needed. That is how fine we need to create our models. And just as we create the model, we keep extracting information from the model as we would be extracting information directly from the system if the model is properly built. Something that it calls my attention is the possibility to build physical or iconic models as opposed to logical and mathematical models. Physical and iconic models are objects in the physical world that can represent the processes that we are interested in. Logical and mathematical models are more approximations and assumptions about how the system operates. Of course, for this we need to have some level of understanding of the theory or the physical representation of the system via some mathematics. Usually you can represent this since it's easier to do the computations, the mathematical computations in a computer program. Usually these logical and mathematical models are used or are solved using computers. It is used to try new things and get results and learn about the behavior under different conditions. Here you have a model for the development of flight, human control flight. The idea was to be able to fly, of course, just like back in the day only birds were able to do. And two brothers, the Wright brothers, decided that the only way for them to develop proper design for the wings of an airplane was to build a wind tunnel. So instead of just trying directly on using their gliders and see what worked or not, they decided to build a wind tunnel. And this wind tunnel was able to generate enough wind into a chamber, and they could stand just on the side of this apparatus, and they tested 100 or a couple of hundred different wing designs, and they measured the drag and measured the lift of the wing parameters, and they played with one parameter at a time, and they were able to very successfully, after experimenting with the wind tunnel, create the most efficient wing profile that promoted the success later, a couple of years later, on how to control the human flight. Of course, with more knowledge and more experimentation and people developing mathematical models, now we have the modern drag equation. It's on the right-hand side, and we understand these from the behavior of different type of profiles, and the coefficient of a particular profile, the area, the frontal area, as the object travels through the fluid, most likely, of course, air in the case of flight. These mathematical models were understood better, and now we can, instead of having to depend exclusively on physical models, we can compute the drag of a profile of a wing based on its physical characteristics represented in mathematical equations. So we have now, thanks to the experimentation in the physical realm, developed the capacity to create logical models about the wing. Here we have another example in which we have the physical erosion created by a river. We can create a physical model just by distributing some sand and pouring water and see what happens and how the equivalent river would form as we keep pouring water through this land. And on the other hand, we can measure different performance of this river using now mathematical models, depending on the type of soil, etc., depending, and we can measure the speed, the position, and erosion that it's happening in these systems, thanks to the fact that we have now a better understanding of the physical world. So, but now we can predict the behavior of these erosion processes using just the mathematical logic systems in the computer. So, particularly for the topics that we are going to be studying, we have some logical models that are very simple to use, or that you have taken courses on, maybe. That includes queuing theory, differential equations, and linear programming. Particularly for this course, since we're studying discrete event simulation, this has to do a lot of how in industrial engineering systems queues are formed and how we measure their performance. So in the most early chapters of the units of this course, we are going to discuss queuing theory. This content of queuing theory is not in the book, but I think it's going to be sufficient for you to understand. Sometimes the models that we have are just too complex for a simple model like queuing theory. Queuing theory, it's a very simplified model. The mathematics around queuing theory are complex, and they get very complex pretty fast in such a way that it's pretty much untractable or very difficult to figure out what the result will be as we keep adding more elements to represent a more complex reality. So we need a more complex model to represent these more complex systems, and these analytical methods like queuing theory does not apply for the more complex systems. So the alternative is to use computer simulation, and computer simulation has a wide range of potential systems to be modeled, as we mentioned. All of them can be used numerically evaluated, and we use software. For the simple models, we can just stick to the analytical solutions. It's faster, easier. You don't need to build a simulation. Sometimes in the projects at school, the performance measures that we want could have computed just by using one of these analytical methods. No need for simulation, and only when it's more complex is that simulation is really needed. One of the advantages of having simulation is that with proper skills, we can represent the complexity of the system, even in the presence of very messy, chaotic, multiple parts playing different stochastic. Stochastic refers to something that is probabilistic. The stochastic events. So not getting blindsided by the fact that it's a difficult problem to figure. We should not look for the answer. We should look for the answer that is convenient and it's actually representative of the challenges that we face. The right solution should account for the complexity of the decision-making process. Another advantage of the simulation is that it takes into consideration uncertainty and non-stationary modeling. What do I mean by that? It means that there are events that happen with probabilistic nature, and those are very disruptive to the system, like the breakdown of a piece of equipment, for instance, or the running out of raw material. And what is the effect of that in the system? It's important in some models, and we have the ability to do that. The non-stationary capability refers to the fact that, say for instance, in a restaurant, the clients do not come the same amount of clients per hour through the day. They have peak hours and hours in which they don't have as many, and just working with the averages of the day will not be sufficient to represent really what would happen if we are planning to, say for instance, determine how many waiters we need or how many tables or what is the expected waiting time for our customers. And as we will see, variability is one of the key elements that we need to consider when we are doing simulation. We're going to talk about more of that when we discuss queuing theory. I am going to stop the discussion at this moment, and I'll bring a second part in another video.